Okay, hello, hello. Yes, can you hear me? Yes. Okay, awesome. Um, okay, so we start again, once again, with the Cosmo Tools session, okay? And the idea is that this is not going to be a talk or anything like that. It's going to be like an exercise that all of us will be doing together. So the first thing, like zero thing, okay? Just to start so that everyone is in the same page. For those of you who have a laptop, please. I guess you had access, so I guess you had read the message that I put in the Cosmo Tools with a link to my drive. Did you? If you didn't, just go now, click on the folder, copy the folder to your drive, and open the Cosmo Tools. Okay, so the notebook. Well, like I'll show you. So yeah, and open the Python notebook, the one that is called like this. Okay, so just go right click, open with, and Google Colab. Do you know what I'm talking about? Were you aware there was a Slack? Do you know that you are in a cosmology school? Okay, I don't know where to start. Sorry? You don't see Cosmo Tools? Okay, so in the general channel, I have put two links actually to that. So in the general channel, general, even though if you look for this, it should appear, but you know, like these things, like it's right here. Okay, awesome, cool. Okay, so then you open this and you will get to my drive. But that's only like view only. So actually you could open everything there, but you won't be able to edit it. So if you want to edit it, you will have to copy it to your own drive. Can you copy it to your own drive? Did you already? Okay, awesome. Thank you for the feedback. That's like 100% working. Okay, cool. So if you do, please go to the first. Okay, so the notebook starts like, well, it doesn't start like solutions. I think it starts with exercise, but whatever. It has like, it looks like this. So you go down, and there's gonna be like a first cell, which is gonna look like this. Just press on the play button. Okay, so that while I'm explaining some things, then like the things are being installed in like in the cloud. Is it clear? Okay, cool. So it's running, I guess, and okay, I can start with the exercise. Okay, I mean, if you have problems, then like one by one later we will fix it. Okay, so let's start with this. So okay, so Cosmo Tools. It's not easy, right, to think of one cosmology exercise that will benefit all of you. So I've done what I know how to do like best. I've used my own work to try to find an example in which at least we learn some things that are useful for like in general for cosmology. So what's the exercise about? So before that. So at the very beginning, I was asked to show you how like this code worked. Okay, so MontePython. But the thing is that you have plenty of examples online on how this MontePython works. Okay, so you can go there and try many different things. So I won't be using MontePython here, even though it's like an amazing tool, but I will be using something that is actually right now being developed on cosmology for cosmological surveys. Okay, so yeah, we will be doing like really like state-of-the-art things that are being produced right now. So okay, fine. So what is the exercise? So okay, the exercise is gonna. I mean, like the assumption is gonna be that someone with a lot of time and a lot of money has gone and has measured positions of galaxies in the skies and redshifts. Okay, so in principle, have an idea of a big volume, big chunk of the universe and positions of galaxies there. Okay, that's what this random guy has done, or lady. So that's so we have like this measurement. So someone has actually make a grid out of that, has computed some density by gridding like these galaxy positions, and has created some density field, okay? And out of the density field has computed some 2-point statistics, okay? So power spectrum, something like that. Everyone fine with the power spectrum, more or less? Do you need any further explanation? It's basically like the 2-point statistics of, of some field, and in this case, a galaxy field, but in Fourier space, okay? That's relevant, because that means that small scales are large values of k, and large scales are small values of k, okay? So you have, in Fourier space, you always have to think backwards somehow. Okay, so this is the assumption. So we have been provided with some data, okay? Awesome. So, okay. So the goal is to extract cosmological information from this large-scale structure data. That's it. That's what we want to do, okay? So fine. How do we do this? So the first thing, once we have the data, the first thing we're gonna need is some model, right? And in this case, since we have like a volume of whatever size, in this case it was like about 1,000 megaparsec cubed, but anyways, then of galaxy positions, what we need is actually a model that predicts how a structure forms in the universe, right? Like how that galaxy, how those galaxies end up in the places where they end up, right? So basically what we need is a model that takes something with no structure, some initial conditions, right? That in principle have like no or very few structure, and then evolves them to something that actually has a structure, right? And this is what I'm writing here, like the density of galaxies is gonna be some function, right, of the density of the initial conditions that we had. Awesome. So how do we do that in cosmology usually, right? So what we assume is like there's some fluid, this is the matter fluid, and then it's going to evolve under gravity, right? But normal gravity, no, not really, right? What we assume is that not only gravity has an effect there, but also like the expansion of the universe has an effect there, right? So the useful thing we assume, this is actually, if you want to know more about this, I wrote all of these things in the notes. And there's like a cool way of getting this, but it's more complicated, and an easy way of getting this, which is the one I'm gonna discuss about right now because it's faster, okay? But the other one is actually more general. So if you are interested, just go have a read about that, and if you like it, then read deeper on that with some references that I didn't provide, but you can find very easily. So okay, so. The idea, very simple. So first of all, the universe is expanding. So you need to redefine your operator somehow, right? Like the differential operators to a reference system in which actually this is happening, right? So this is like the things on the left, and that translates, well, and then you're gonna use some conservation laws like the mass conservation and the Euler equation, right? Like conservation of momenta, and also the Poisson equation. Anyways, you don't have to know all of this. So this is what it's used, okay? Fine. Now, if you do this, if you substitute these operators there, then you end up with a couple of, master equations that if you want to know how the structure is in the universe today, then, you have to solve. That's it. Problem, there's no analytical solution to this, okay? So how do we proceed? So we either linearize the equations, okay? So we perturb the solution in a perturbation series, and we just stick to the first ones. And then if you do that, you realize that actually like all of like the terms that were coupled, decoupled, because anything that is second order, you're going to throw away, right? And then they become linear equations, and you can actually substitute. You can do a little bit of algebra with them and find an equation, which is this one, that actually has some analytical solutions. Okay. Now, how the initial conditions are and so on, that depends on Boltzmann codes, and well, I won't get into that. I don't know if Mateo Biel will get into that in his lectures, but anyways. Point is that you can, in principle, like the linear solution, you can actually compute it fairly easily. No, I mean, not super easily, but fairly easily. Or you can actually put these equations into a computer and wait for the computer to solve them, right? And usually what we do, what we do with that is actually these n-body simulations, right? Which I already showed a picture of that, in which you have like several particles and you allow them to evolve with this gravity, right? So then you start with some homogeneous initial conditions, you allow them to interact through gravity, and then you end up with some structures, okay? What's the problem of this second option? What's the problem of this full solution, right? That is very computationally expensive, right? We cannot use it many times. We can compute it, like tens of times or something like that. But if you really want to extract cosmological information, what you want is actually something that you input some cosmological parameter, and very fast it gives you the answer that you're looking for, right? And this is not what one can do with n-body simulations. So but there's a way forward, which is train a neural network to actually interpolate between many results that you had before, okay? And that's called an emulator. And actually, this is helping a lot right now in cosmology to extract like new information from data. And that's what we will be using today, right? So we were going to use like an emulator that has already been trained on full nonlinear solutions and also on linear solutions. Because even though I told you that this was kind of easy to do, the truth is that to really compute this, not to solve this specific equation, but this equation with all of the complicated things that you need for a Boltzmann solver, actually it takes few seconds. Few seconds doesn't sound like a lot, but for an exercise that we have today, like this 2 hours long, we cannot do it. Okay, we just cannot use it. So the emulator is going to be an emulator for the full nonlinear solution and also for the linear solution. Okay, so we will be using emulators for both. But in this case, you don't have to worry a lot about like where the theory is coming from. You just have to worry that you just have to know that you have like two models. One that is fully nonlinear, so computing completely the equation of evolution of a structure formation, and another one that is an approximation, and specifically a linear approximation. Okay, good. Which emulator are we going to use? The only one I have experience with, well, that's not technically true, but this Baco emulator. Okay, so an emulator that we produced. Okay, so fine. Part 0. Okay, just to check that everything is working fine. Just open, as I was asking you, this notebook, this Google Colab notebook. Okay, and let's run until the point that I put here. Okay, so until you see basically like this, this plot. So. Yeah, so anyone, now is the moment, right? Like anyone had a problem running this cell, which is the installation cell? I guess you have to have a problem. but anyways, let's see. So did it run fine? You were not so shy yesterday in the in the cocktail. Okay, so it I guess it has run. So if it ran, then probably it's asking you, like there's like this little piece which is written somewhere like restart runtime. You have to restart runtime. Okay, you have to click here and say yes. Otherwise, like everything that you have actually installed won't be there. I mean, if you want me to do it, yes, Thomas? Because for me it says like module Google is not there. Like at the first time, but it installed. Okay, so you play this and it told you Google. Did you copy the folder into your own drive? Yeah. Okay, and it's telling you that Google. Okay. No, that I know of. You mean this content drive, maybe, or I don't know. Let me have a look if it's happening to you. Yeah, for the rest, just keep running the stuff. Okay. I don't know, but this is because you're. I mean, just open it. Okay, sorry. Let me show you in here. Sorry. Okay. So what you have to do is the following. So once it is in your drive, okay, you go to the exercise and then you say like, okay, right click, open with Google Colab. Not, I mean, don't run it in your own notebook because then like this pip install, won't work. Yeah, yeah. This is so that you don't have to install it in your own machine. Okay, but you can do it afterwards in your own machine if you want to. Yeah. Okay. Anyone else having like specific trouble with this? Okay. Okay. So I'm not sure because I am in my own drive and that's complicated. But I mean, I think you can do it with the right click, copy, copy, copy. Maybe not. Make a copy. Make a copy here. Okay. But you have to copy the full folder, okay? Because I also include some like the data. Okay. So in principle, what I will do is I will go here. I will say make a copy somewhere. Move to. No, move to no, because you cannot move it, of course. Make a copy. No, I don't see the make a copy. Do you see the make a copy from here? Mm. Beyond the files. Wow, that sounds. Ah, selected. Ah, okay. No. Yeah, we could do it, but I'm pretty sure that you can do it without doing that. Now I have a. No, that's my question. Maybe I can. Well, no. I mean, the thing is that I can move it. Mm. So anyone is having problems copying it because I don't know how to do it. Okay. Okay, but that's another way. Yes, that's another way. That's very smart. Yes. But there should be a way, right? Mm. Ah, wait. Here, maybe. Hmm? One by one, but that's super uncool. Yeah, yeah, yeah. Okay, that's yeah. Sorry about that. I didn't know it was so difficult to do this. But I have done this before, anyways. Ah, there's gonna be like some error messages appearing. No, not a problem. Okay, did the first cell run for everyone? At least the first installation one? Yes, yes, yes. I like that. I like that row. It's very, it's very good at this. Okay, I'm gonna give 2 more minutes, and then you tell me. Yes, Thomas. Yes. Oh, locally, okay. Okay. Yeah, for the Google. Yeah, the last ones, right? Yeah, these ones. Yeah, but then you're installing like all of these things. I mean, if you don't mind having several gigabytes of things in your computer, then it's fine. Yeah, but in any case, Thomas, maybe like another option is to copy these ones, right? Like select all of them, and then copy. But then put it. If you put it into your Google Drive, then you can use this Google Colab if you want to. Okay. Then like no. Okay. 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 Cool. I mean, if it works like that, awesome. Ginebra, tú ayer sí que te copiaste la esto. ¿Cómo lo hiciste? Era fácil, ¿no? El folder. Y lo subiste. Y lo subiste. Vale, vale, bueno. Vale, vale, debería haberlo mirado antes. Sí. No es muy buen error, ¿eh?
No sé si lo conoces. Diagnosticar esto es imposible, ¿no?
Es imposible. ¿Cómo lo has abierto? ¿Y cómo lo has conseguido?
Cuando me pide conectar a...
Sí.
Perdón. Es el último comando que conecta a mi Google. Me pide una autenticación. Le voy a conectar y me dice something stupid.
Vaya. ¿Por qué no te puedes conectar a tu propia Google account?
No lo sé.
Vale, esto no me lo esperaba. A ver. Ahora. Vale, perfecto. Me encanta. Los mejores tipos de problemas, los que se solucionan solos. Okay, awesome. Okay, so I'm gonna assume that you kind of, like you were able to do this. You will have like longer time afterwards, okay, to do this. Remember to restart runtime, otherwise, really, it won't work. So fine. Can you then run this one, like the second one, which is, I mean, it depends on the path in which you have put your like the data. Well, whatever you downloaded. Okay. Okay. So cool. So this is just a way of reading the data and plotting the data. Okay. Nothing fancier than that. So now, how to call the model? Okay. So this is basically a line that, as I was saying, like just imports the emulator that we will use for both models, the linear model and the fully nonlinear model. Okay. So you just click play. And then it will load a couple of emulators needed for it. No? It did? Yes? Okay, so the path, right? Okay, awesome. So the path is the path to your drive. So wherever you have put your like this, like what you copied, it has to be like probably content and drive. That's going to be the same. My drive probably is going to be the same. And now you will have like either Colab notebooks or just Winter School. If you want, I can go and check what's the path and then tell you. Me caigo. Sí, vale. Perdonad. Sorry. I'm sorry. Okay. So. Okay.
But I'm not sure.
Just go to your drive. Maybe it's. Where's your drive? Where's the folder in your drive?
Just go back.
No, otra pestaña.
This one.
Okay, so this is, vale, mi unidad. Es que lo tuyo está en castellano. Perdona, es que el mío está en inglés. Entonces, claro, tienes que escribir, o sea, es lo mismo, pero tienes que poner mi unidad en vez de my drive en el otro, en el... Bueno, bien hecho también funciona. Ahí es mi unidad. Okay. Okay, so if it's in a different language, then it won't be called like my drive. Perdón. Sí, perdona.
Yo tengo el problema aquí, no me encuentro
Google Colab.
Colab no tenemos.
Vale.
Es como si no tuviera...
Vale, eso es normal. Porque o sea, tú lo tienes en el mío Drive. Sorry, I'm speaking Spanish, but is that fine?
Sí, habla español.
Vale, vale. Pues entonces, es que el path que tienes que poner, o sea, como has copiado el folder a tu carpeta, el path tiene que ser el drive, el normal, y después el mío drive, y es el path a la carpeta que tienes. Están aquí los archivos. Son estos. Vale, pues solamente tienes que poner hasta el mío drive. Vamos un momento al notebook. No, perdona. No sé dónde está el notebook. Lo tenías abierto, ¿no?
Ese es el tuyo.
Es el mío. Vale, pues...
Este es el mío.
Vale, pues vete al tuyo. Es que del mío no vas a poder...
No, yo estoy aquí.
Vale, doble clic al el ejercicio.
Se me abre así.
Vale, pero se te abre así. Vale.
Si yo hago doble clic, me dices que se lo quiero descargar.
No, es que ese es.
Y me lo abre así.
Vale. La verdad es que con Mac no tengo ni idea de cómo funciona. o sea, tú has hecho doble, o sea, clic derecho y abrir con Google Colab, ¿no?
No me encuentra el
A ver, open with.
Pero no lo tengo aquí.
Pues no lo sé, perdón, no tengo ni idea. La otra opción es que te lo instales o sea, en tu ordenador concreto, o sea, dentro de tu laptop, con los pip install que están ahí, lo mismo pero en tu ordenador. Lo que pasa es que lo que no quería era llenar vuestros ordenadores de un par de gigas de cosas. Por eso no lo hice así. Perdona, no sé cómo funciona. Sí, lo que pasa es que después voy a dar tiempo para escribir algunas funciones, igual te aburres. Si no, júntate con alguien y lo haces juntos, sí. Vale, perdonad, gracias. Okay, so I'm going to assume that it's kind of working for everyone. I know some of you are going to go faster than others. That's life. Okay, so yeah, as I was saying, like it's very possible that you have to change this path, right? Because now it's to your drive and not to my drive. That doesn't mean that you have to put yours here. No, that's just look for your own path. Anyways, so these are the data. Fine. Now the model is imported like this. Cool. So let's compute one model. Okay. So let's compute the model for a given cosmology. Okay. So this is how it works. Okay. It's just you define some cosmological parameters. And the ones that I have provided already in the notebook are actually the true ones, okay? So I know the truth of the universe because I made this universe. So the data that I provided actually is data I created. So I know the exact cosmology, and we're going to use this as a test example to know if we can recover the right cosmology, okay? It is the right cosmology. Anyways, so this is the cosmology that we will have to compare to. Okay, and then the way of calling the model is super simple. It's just this line here. Okay, it's just emulator.getLinear. This for the linear model. And now this is just a plot to show how it looks. Okay, for the nonlinear model, exactly the same thing. Okay, so let me open it. Exactly the same thing, but instead of get linear model, it's get nonlinear model. Oh, so imaginative. And then like we can plot that model. Okay, so let me run these two. I think I already ran this one. Yeah, I forget which ones I ran and which ones I didn't. Okay, so I ran this other one. Okay, so now I have like given the true cosmology, the model, the linear model, and the nonlinear model. Okay. And the first thing I do here is basically I compare the linear to the nonlinear. Okay, the linear to the nonlinear model, and actually you can see here that the difference between the linear and the nonlinear is actually the amount of clustering that there is in the smaller scales. Remember, we are in the Fourier space, so large values of k means smaller scales. Okay, so you can see here that actually the amplitude of the power spectrum, meaning like how many of those scales you have, is way larger in the nonlinear model than in the linear one. Okay, So it's predicting that actually you have more clustering on small scales. And that's the main difference between nonlinear and linear, together with some others. Okay, so now let's do a comparison of these models with the data, okay? And that's where where like the zeros, let's say, let me run this one. I already ran it, anyways. Well, the zeros exercise finishes, okay? So until here, you have everything, right? This is an example on how to how to read the data, how to call the model, and how to plot things, basically, okay? So fine, so this is what we get, and do you find something surprising? So I used the exact same cosmology, and I used like 2 different models. Are the models are the models very good with the data that I provided? Like, do they fit amazingly good the data? I hope your answer is no. Okay, so exactly. So it's not. I mean, it's of course like there's something missing, right? But what are we missing? So 2 key ingredients. I told you that that this data was galaxy data, right? Which means that I'm not giving you the full matter distribution. I'm giving you just tracers of the matter distribution. Okay. So how do we model in a linear way? Okay, I'm not gonna get more complicated than this. This relation between tracers of the field and the matter field itself. Okay. So the thing that we have plotted is actually this object. Okay. So this power spectrum, which actually I forgot to put a sub m here, but it's the same as this one. Okay. So it's this power spectrum. That's the one that you have plotted. Now, if you trace that one, actually the connection between both, and you can again like go to the notes, and I have like a brief explanation on why this is the case, is like through this linear bias parameter. Okay, so this linear bias parameter is in principle a free parameter, even though there are ways of trying to compute like the range in which it should be. Okay, so and that will be like the first step that we are missing, but that's not the only thing we are missing. So there's also an extra effect, which is the fact that we don't measure directly positions of the galaxies, right? When we have like a survey, what we measure is actually positions in the sky and redshifts. But the redshifts are affected by Doppler effect. So if the galaxies have a velocity, that means that there's going to be like a Doppler shift, and we might think that the position is actually shifted to respect to the true position. Okay, so this is called redshift space distortions, and the way of modeling them is actually through the Kaiser effect, and I'm showing you here like the equation. Okay, so it's basically again it's something like some polynomial times the power spectrum that we have in the model. So good, if we put these 2 things together, then the equation that we should be using is not just the power spectrum that we were using before, but this this function, okay, these 3 parameters times that power spectrum, okay. So fine, so that's the exercise. You have your power spectrum. Just code this equation up. Remember that this beta and this bias are free parameters, and play with these free parameters by hand to check if you can get like a better fit than before. Okay, so that's what you should do if you want to. I cannot force you. Just try doing this. Okay, I'm gonna wait. Yeah, like 5-ish minutes, 5 to 10, something like that. And please let me know how it's going. By the way, if you're very lost, I also put the solution in the same folder. So if you really don't know how to start, just open the solution and you will be able to see how I did it, okay? Which doesn't mean it's the best way. Yes? Okay.
Me sale esto.
Ah, vale. No le has dado. Okay, so go up a little bit. Oh, whoa, you went too much up. There should be like a runtime clicking thing here. I guess you You did?
Yes.
Okay, here. So you did rerun this?
Yeah.
Okay, so yes, and then go back, go down. Okay, and then you play it, and then it tells you, I don't understand what's going on, right? Ah, fixed. Yes.
Tengo el mismo problema.
Sí, vale.
Entonces, pienso que es porque no le estoy poniendo bien la ubicación. ¿Cómo puedo saber
A ver,
que
déjame
cambiar
mirar.
mi nivel?
¿Puedo mirar cuál es el...? Es que no veo nada. Tienes el brillo un poquito bajo. Perdona, soy un cegato. Vale, ¿puedes bajar un poco para que vea el error?
Dice que no se encuentra eso.
Vale, no lo encuentra. Entonces, content drive, mi unidad. Es que claro. ¿Y cuál es el path? Es que claro, en castellano no tengo ni idea de cómo se llama drive. Pero también se llama content drive o contenido drive. Es que claro, no lo sé. Es que no lo sé. Pues no lo conozco, la verdad.
Y entonces aquí trataba de ver ubicación.
Nuestra ubicación, ¿vale? A
Pero
ver.
no me sale.
Ahí.
Se quita.
Me cachis en la mar. Vale, es Winter School 2022. ¿Podemos volver a mirar el path? Seguro que lo tienes bien, ¿eh? Pero... Vale. Content drive. Data Winter School.
¿No será porque aquí este no me lo subraya?
No, yo creo que no. O sea, suele funcionar con eso. Data Winter School. Sí, yo creo que ese es casi como lo llame.
No.
Mm,
Esta. Ah, vale, me fijo.
a ver, podemos mirar, pero estoy bastante seguro de que le llame así. Sí, sí, le llame así. Ujú.
Vale, pues entonces voy a seguir checando esto porque debe de ser acá.
Podemos mirar, vamos a buscar en Google el nombre o sea, path del drive en castellano. Vamos a buscarlo. A ver, igual lo puedo mirar hasta en el móvil.
A ver,
Perdona, es que no lo sé. Te lo traduce él. Qué sinvergüenza.
Pone Google Drive.
Lo mismo, ¿eh? Mm,
Aquí en ver detalles no sale Drive.
Es que hay otra opción que es un poco fea. Pero puedes abrir No, pero quiere decir que puedes abrir el TXT, copiar los datos y hacer un array con eso. Pero es un poco feo. Sí, claro, que tú o sea, lo copias y a mano lo pones como un array y ya está. Es una opción, pero no sé cómo... La verdad es que no sé por qué no lo encuentra. Podemos, o sea, porque al restart runtime y todo eso lo has hecho, ¿no? O sea, eso no era problema. O sea, lo que te he dicho, tío.
Sí, bueno, tal vez también le falta lo de...
Pues vale, podemos volver un momento, solamente para comprobar que no sea esto. ¿Puedes subir un poquito? Vale, aquí, explora un poquito hacia arriba. Ay, no tanto, un poquito más hacia abajo creo que era. Hay un cartelito un poquito más hacia... Ahí, Restart Runtime, dale. Dale aquí así. Vale, ahora vamos a volver a intentar correrla de abajo. A ver si hay suerte. Qué rabia.
vale, no te preocupes.
Search Stack Overflow. Mira, se puede poner ahí Search Stack Overflow. Dale, clic a eso, a ver. No hay suerte. Ya, perdona. Sí. Sí, Francesco. Dime.
Aquí cuando dices cuál es el maximum fitting mode por cada uno de los modelos, significa por el lineal y no el no lineal.
Sí, eso es. Sí. Ujú. Okay. So one question: who's finding this boring? In the sense of like, I mean, no, please don't be mean. I mean, like really easy, right? Like who's already like in the fourth exercise or something like that, in part 4 or part 2, part 3, whatever. I'm telling because like I have ways of making it more interesting. Okay, good. Then then go ahead. Yes. Yes. Mhm.
I mean, you can just feed the overall factor.
Yes.
You cannot separate.
Actually, we will get to that because actually beta is not really independent. But we will right now we're going to assume that it's independent for the specific reason that we will do a Markov chain afterwards, and that's going to mean that we're going to compute this many times. And actually, the function that relates beta and b is not very complicated, but heavy enough that it will take a little while. So, but yeah, well, let's assume by now that they are two independent free parameters. Anyone having like any very specific problem that I can help with? Okay. Yes. Sorry, this always happens when it's like the Cosmo tools. Okay, yeah, this is happening. Okay, but what's the problem? What is the error that is giving you? Okay, no, the path not found. Okay, okay. So in principle, yeah, the problem. Okay, Drive. Okay, that's not the language I control. Okay, so what is the path to there? In principle, it should be something like. Can you open the notebook, please? So it should. Okay, so content drive.
I don't know. I know that it's content, but
Okay, and you don't think you. Okay, so it doesn't go with my drive, and with Mon Drive.
no.
No.
Mine worked with an extra drive here.
Yeah, that's.
And then drive. And then
And maybe that's what is missing there. 1 second. Sorry. No. Okay.
I mean, I changed it a bit.
Yes, but it worked or it didn't work.
But I changed it a few times, but then I think it wasn't working. Oh, I have downloaded. I'll open everything.
Yeah, but you're opening it with your own.
Yeah, no, but
Yeah, I mean, if
because I downloaded the original.
okay, but then I mean, I would really suggest to use the Google Colab. Okay, okay, awesome.
At first I downloaded it.
Okay, okay.
Just to see it.
Okay, cool. Yeah, whatever the exercise or the solution doesn't matter.
No, it was a very content drive.
Okay. So it worked. Okay. I thought it didn't. Yes.
Also, you can use ls in the cell.
Right. Where are you? Right. That's true. I forgot. with a question, with a exclamation mark, right? Thank you very much, guys. Sorry. I think I might know how to get the path. So open. No. Like go to the Google Colab. The one you en el que estabas. Vale, ahora más código arriba a la izquierda y ahora vamos a poner exclamation mark, o sea, la de exclamación, el de estar sorprendido. Sí, ls. Y córrelo con el play si quieres o con como quieras. Vale. Ahí es donde estás. Drive, sample data. O sea, ahora mismo este Google Colab está en ese sitio. ¿Están los datos en el mismo sitio? Vale. No sé por qué le aparece otra. O sea, y ahí también está. Bueno, prueba ese path, a ver si. Content. Y también te sale Drive y Sample Data. Vale, no sé. Pues entonces igual no funciona con eso.
No, pero no te has movido de carpeta, ¿sí?
Ya, no sé, es un poco extraño. Ok. Sí, pero no estoy seguro de que vaya a funcionar. Perdona. Is it working for you guys now? No, no path, right? Why is so complicated in different languages? Where is Drive? So, yes. I mean, in principle, you can do what he was suggesting, like just exclamation mark ls, and it should tell you where you are. But but it's not actually working.
You can do like tab and like it will show you like the available directories and you can find.
Can you help them, if you don't mind? Thank you. Sorry, guys. Because I don't know. Okay, so 20. Sí. Ah, vale, sí. Sí, es un poco extraño. Vale, bueno. Hello? Ah, yes, okay. Okay. I guess you got some some values. Maybe not. Maybe you're still trying to run this. In 10 minutes is the coffee break. Yay! Uh, let's. Okay. So I guess what you should have found it's something like what I'm showing you here, right? So you're able to get some beta and some B that is able to fit kind of like reasonably well, like these large scales, and then departs right from the true from the data, right? Okay, so I mean like this one works much better, right, than before. Now, which one, like by eye, which one would you think actually works better, the linear or the nonlinear model? By eye. Yeah, looks better, right? Let's find out if this is true or not. Doing something way better. Okay. So now what we're gonna do is like MCMC. Okay. So Markov chain Monte Carlo. So instead of doing this by eye, what we're gonna do is we're gonna run like just like some code that actually finds the parameters for us. Okay. Now, I don't think I can explain very well MCs in such a short time. So what I have done is I have put here 3 YouTube videos that if you see them in a row, then you know everything about Markov chain Monte Carlos. They are not very long, each of them, and they're really well explained. So yeah, like my suggestion would be just watch them, not here, but if you're interested, watch them somewhere. And I'm gonna give you like a very, very super stupid brief overview of them. Okay, so let's say that you are in a parameter space that has like this omega baryon and omega matter. I think it is. I cannot read it very well. And then you have computed the likelihood of your data, of your model being like a first sample of your data at, I don't know, let's say like this point, okay? Now, you change both omega matter and omega baryon. And you are now in like a new point in your parameter space, so you compute your likelihood again. And then let's say like what could happen, right? What could happen is that the new likelihood is actually like greater than the old likelihood, which means I'm gonna keep this point, okay? But it could happen the opposite, right? It could happen that that new likelihood is actually lower than the old one. Then if this happens with a given probability, that could be 0.5 or not, I wrote here 0.5, you keep it or not. And then you keep doing it like over and over and over until you sample like all of your space, and then you get like the posterior distribution, okay? So the probability of your parameters to have some values. Okay, fine. So with this horrible explanation of what MCs are, this will be like the next exercise, okay? So you're gonna have to write a chi-squared function that gets as an input some cosmological parameter. I suggest it to be omega matter because it's very sensitive to this power spectrum. But in principle, you could choose whatever other you want. And the two free parameters that you have played with, which are like the B and beta, and also some k max, okay? Some maximum value of k to which to do the fit to. Now, there's an example on how to run an MCMC in the notebook, okay? This is like a very toy example that it should be somewhere here. Find beta. No, it's not this one. Yeah, here. So so we're gonna use a code called MC. Okay, and in principle, it's not difficult to use, but it's not the most straightforward one. So I put in the notebook two functions that makes it super easy to run. Okay, and now like the example that I put here is just a data that is like 1 plus 2x plus 3x squared, and the model that is a plus bx plus cx squared, and then I show you like how like a wrong values of a, b, and c would look like, right? Then how to do the MCMC, which is basically like this line. Okay, this is an example that you have in your notebook, so no worries. You can go through this. And then after the MCMC, I show you how to fit the best fit, how to put like the maximum likelihood parameters there, and how the 2D contours look like using this corner function. Okay, and you can see that it was a very simple example, so it recovers perfectly well the numbers 1, 2, and 3. Okay, with no biases and so on. So this is just an example. So the point is, you follow this example to basically know exactly how to, like how this works. And once you know how this works, then you will realize that what you need to do is actually to define a function in Python in this notebook that computes this chi-squared. Okay, so basically computes like it takes the data, it takes the model, it takes the errors, and then it computes like the sum of all of this data minus model over the errors squared. Okay, and that's it. That's the next. That's the next exercise. Again, you have the solution. If you are very lost, please go ahead and check the solution. Okay. Yeah. And now let me try to fix all of the problems that there are from before. 2 minutes for the coffee. in half an hour. In half an hour, we come back from the coffee break, okay? And we keep doing this. Okay, hello. Okay, so I guess most of you already have like the chi-squared function working, and you got something similar to this, right? When you do the best fit and when you get like the values of the omega matter and the linear bias, right? Okay, so if you did this fit down to scales of about k max 0.1, then yeah, you should have like something very similar. Now like the next thing is, and some of you actually have already found it. Try to find the k max. Okay, so I told you like to do it until k max of 0.1. Try to find the k max in which this model actually breaks. Okay, so the idea is just try to to do the same fit that you have done until now, but changing the value of k max. Okay, so fit until 0.1, until 0.2, 0.3, whatever you want, and then do basically like the two plots, right? Like the best fit and the contour plot, and then you tell me what you find. Okay, yeah, it's I mean, in principle, it should be easy because repeating the same thing, right? But for different k maxes. And now let me go down and help you with this. Okay. So I'm going to assume that you already got this. Maybe it's a big assumption. um, okay. So what have you found roughly? Have you found like which is the value of k max in which you think that this linear model breaks? What would you say your guess? The solution is in my back, but I'm asking you anyways. I can stay silent for a very long time. No one has any guess of what is the K max. Yes, I see a 0.1. Well, roughly, yes, but like between, I will say, okay. So let's look at the results that I got, and probably you did get too. So in principle, if you stop at k.1, that's the orange line, right? And even though there are like some oscillations, right, still within the error bars. So in principle, you will say, yeah, it's kind of fine. And if you go to the cosmological parameters, the orange is actually within 1 sigma of the true omega matter value, right? So in principle, yes, 0.1 works. Now let's go to 0.15, right? 0.15, you go to the best fit, that's the green line, and still is within the error bars, not super within, right? There's like a couple of points that might be outside. And then you go to the parameters, and you see that it is about 2 sigma away. Now, is 2 sigma a good or a bad thing? In principle, it could be, right? Like 2 sigma is like not that bad. I know it is a bad thing because I know that I over-predicted my errors. But in this case, like in the exact case that you have, it could still be reasonable, right? Now, if you get from 0.15 to 0.2, aha, my friend, that's super biased, right? That's like at least 3, 4, 5 sigma away. So clear detection that our model is wrong. That's another way of putting this. Anyways, and on the best fit, you see that too, right? That it starts failing. Like the linear model tries to fit those places where the error is like smaller, and by like really under predicting the other ones. Okay, nice. So this model completely breaks down, right, at those scales. And of course, what is going to be my next question? Not this one, this one. Can you repeat exactly the same thing that you have done, but with a nonlinear model? And then you answer the same question. So now the idea is that, like we went through all of this thing of running embodied simulations, getting results from them, getting like this neural network and interpolate over them. Now tell me if it was worth our time. That's like the question. So try to do exactly the same thing, but substitute the linear model by the nonlinear model. You have 10 minutes. Okay. Okay. So yeah, let's assume that you did the exercise with a nonlinear model. Now, did it work better than the linear model? That's my question. I know it worked slower. Yes, it worked better. Yes, awesome. So what's the maximum scale in which it failed? More or less, roughly. Order 1 already? Order 1? Oh, that's amazing. I'm surprised. I only tested until 0.3, but amazing. 0.7. Yeah. Then I'm not that surprised. Okay, 0.7, fine. Okay. So amazing. So even though we use like linear recife space distortion and linear bias model at the level of the monopole, it seemed to work right until lower scales. So okay, fine. By the way, just to let you know, it worked because the error bars that we used are actually a little bit big for what the data really is, and because we are only testing at the power spectrum level. If we will be test at like different multipoles, like quadrupole or hexadecapole, or different statistics, like 3-point functions, it will break way earlier. Okay, but anyways, it's cool. It's cool that we got this. So. And now, like one of the things I was asking you to do was to plot like what is like the error you get in omega matter when you measured each each scale, right? And I guess I mean you should find something similar to this, like the error as a function of k max, it decreases. Okay, so if you use very large scales, it has like some value, and if you include more and more modes, like more and more values of k, then you see how it decreases. So would you say it makes sense to try to push towards smaller scales? Like in principle, yes, right? Because you're really like pinning down more and more your cosmological parameters. So in principle, like given some data, it's always good to be able to make use of the full set of data, right? Yeah, so in principle, it's worth, right, doing this, and that's like one of the things I wanted to tell you with this exercise. Like it's worth doing work on the modeling, because it's true that we need more and more data, but it's also true that we need more and more modeling. Otherwise, we will be just throwing data away, and we don't want that, right? Okay, fine. Yes, I think there's okay. So this is like the discussion I wanted to have. I know I kind of like answered the questions for you. Sorry. So yeah, like this is just extra credit in case you want to do it at home or whatever. Just up to you guys, because it's really late. We haven't here for very long, but we have assumed that this beta parameter is a free parameter. But the truth is that it is not a free parameter. It's actually the growth divided by the linear bias. So even though you assumed 2 free parameters, we only had 1, okay? So there's one way of actually computing this, okay, with the emulator that we have been using, which is, as I showed you there, through the growth factor. Sorry, through the growth factor and through the growth of a structure, this D of A, okay? So you can actually, like code that, then remove that beta and substitute it by the expected theoretical value. I did that for you, and I got the results that I'm showing you here, which are basically the same results. And that's why I didn't ask you to do this, because I knew we were going to get something very similar, because everything is pretty much consistent at this level. Okay, and I think that's it. I think you still have, like, if you want 10 more minutes, and you can ask me questions and these kind of things. And I believe Carlos wants to say something about the Slack channel. No, I do want to say something about the Slack channel. Use it. That's it, right? That's it. Check it. Check the Slack channel. And if you have any questions to like about anything, please feel free to ask them to access there. Yes, I knew Carlos wanted to say something.
Since Marcos is provoking me, just a brief summary about tomorrow's. So tomorrow we're going to have seminars, lectures during the morning, and then in the afternoon we're going to have this this, if I recall correctly, the program, no, it's not tomorrow, it's going to be on Thursday, by the way. This is just making you aware of what we're going to be doing on Thursday. Thursday, in the afternoon, we're going to have this pen and paper session, right? We're going to be split in 2 rooms. So there have been, we have been shuffling you in 12 different groups so that we mix you as much as we could in terms of gender, in terms of expertise, in terms of your home institution, so that you know, you mix efficiently. And then 6 teams will be working in a room which is called Cosmolab in this building. Another 6 teams will be working in the IAC headquarters, this building here, in the aula, right? And the idea is that, so you, the tutors, yeah, you and 3 more people, you have to split, right? So you are 4 guys, so 2 people go in one room, and 2 people go to the other room. And then you essentially, we have uploaded the problems that some of the lecturers have provided us with in the Slack channel. So please check the Slack channel, because there you will see the teams, to see what team you belong to, and then you just check the problems, and then you have to agree. First, you have to spot the other members of your team, which might not be trivial, and then we'll leave this up to you, and then you just agree on which problems you want to address, and then you have like have some time to start trying the problems, and then you can share the solution. You have some feedback from the tutors, so that's the idea, right? That and then you have access to whiteboards, and you can discuss. If ideally is that every team is self-contained in the sense that each team has like 5 or 6 people. So yeah, so since you have different expertise, you should be able to address all the problems. You have to agree which problems you want to address. But if you want to have some communication inter-team, that's also possible. That will leave this up to you, okay? But yes, I tell you that the problems have been uploaded in the Slack channel. The team membership has been uploaded in the Slack channel, and you should just check it, start reading the problems, start thinking about them, so that you can really profit this pen and paper session for Thursday, okay? And then, yeah, as I said, the tutors, you just agree which, whoever wants to stay here in the museum, just as you wish, just do it as you prefer, okay? Any questions? Not? Well, you have some, a few hours before that meeting. It should be on Thursday evening, right? Afternoon. Okay, so thank you, everyone. I'm gonna, I guess, yeah, thanks to Marcos, who was putting a lot of effort on this, and the rest of the tutors. Yeah, thank you, Marcos, for taking care. Really, this was, I think, it turned out to be a very nice and useful exercise. Yeah, so.
Ask me about the exercise at any point in these 2 weeks. I'm gonna be here.
All right. So take some rest, and tomorrow we'll resume here at 9 a.m. See you.